Hello, my name is Vyjidacek and the topic of my presentation is revisiting the GreCon algorithm for Boolean matrix factorization. First of all, I am going to talk about basics of Boolean matrix factorization. Then we will move to description how we redesigned GreCon algorithm, and on small example I will show you how it works. And after that I will talk about experiments, and finally I will say a few words about future research. Let's move to the basics of BMF. Let I be a Boolean matrix. Our goal is to find matrices A and B such that if we multiply A and B, we will get matrix which is equal or approximately equal to matrix I. The multiplication of two Boolean matrices is similar to classical multiplication. We only exchange addition with minimum function and multiplication with maximum function. Matrix equality is defined using number of ones in the matrix, and quality of factorization is measured by metric E. Using this metric, we measure number of uncovered ones. Now I am show you how we can use knowledge of formal concept analysis in Boolean matrix factorization. Let's begin with formal context. Formal context is structure with three items: x, y, and I, where x is set of objects of size m, y is set of attributes of size n, and I is incidence relation which says object x has an attribute y if this tuple is in I. This structure can be seen as Boolean matrix, both I, where matrix item at indexes I and j is equal to 1 if tuple small x and small y is in the relation I. For such Boolean matrix, we have associated pair of arrow operators. We call them simply arrow up and arrow down, where arrow up takes subset of object and as an argument and returns the set of attributes which are common for all objects. Arrow down is defined alike arrow up, but as an input it takes subset of attributes and returns a set of common objects for all attributes. Using these arrow operators, we can define formal concept. Let's take sets C and D, and if C arrow up is equal to D and D arrow down is equal to C, then we say that tuple CD is formal concept and the set of all formal concepts for formal context is set of tuples CD which satisfies definition of formal concept. Now let's F be a set of formal concepts. If we add fixed indexing into the F, this set induces Boolean matrices AF and BF, where AF IL is equal to 1 if I is in CL, and 0 if I is not in CL, and BF LJ is equal to 1 if J is in DL, and 0 if J is not in DL. And L is from 1 to K, where K is number of concepts in the set F. This set of concepts we call set of factor concepts. Now we have all needed information to start with description of GreCon algorithm, which is simplest algorithm based on formal concept analysis. It uses greedy strategy to compute matrices AF and BF. As first step, algorithm computes all concepts, for example using fast close by 1, and in each iteration, algorithm computes for each concept current coverage of not yet covered ones, and selects concept with maximal coverage as factor concept. Using this simple idea, algorithm computes exact or approximate from below factorization. The most consuming task in GreCon is that we need to compute current concept coverage in each iteration. Our new version, called GreCon 2, does not need to compute this coverage repeatedly. We store this information in data structure, and if algorithm selects new factor, then other concepts coverage is updated. And GreCon 2 takes matrix I as an input and returns set of factor concepts. Let's look at the pseudocode of GreCon 2. As I said, we have matrix I on the input and the set of factors concept on the output. Firstly, we need to compute all concepts like GreCon. Then, for each concept, we compute actual coverage and store it in array covers and create item into the array called cells, where we store for each item in the matrix I which concept covers this item. Now we are ready to start with factorization. We need to select concept with maximal cover, and for each tuple ij, we decrement actual coverage of each concept which covers tuple ij. As a last thing, we remove all information from our structure about selected concept, and we repeat this while we have some uncovered ones. Now I'm going to show you GreCon 2 computation on little example. Let's have X as a set of objects and Y as a set of attributes, and I is Boolean matrix associated with formal context. Firstly, we need to compute all concepts. This context contains 6 concepts, and for each concept we compute actual coverage and store it in the array covers. The next step is to compute array cells, where we store information which concept covers which item in the matrix I. For example, item 0a is covered by 4 concepts, 1, 2, 3 and 4. Let's start with computation. On the slide we have table with 6 columns. In the first column we have concepts index in the array concept. The second column contains intent of this concept, and in the third column we have initial actual coverage for each concept. The empty columns will contain coverage after first, second and third iteration. In the first iteration we select concept 1, 0 and AC. This concept covers 0A, 0C, 1A and 1C. For each tuple we get concepts indexes which covers this tuple. For example, 0A is covered by concepts at indexes 1, 2, 3 and 4, and we decrement coverage for these concepts. Now let's look how actual concepts coverage have changed. Coverage which change has bold font. The selected concept has intent AC and coverage after first iteration is equal to 0. We also need to remove this concept from cells, so we can't see concept index 4 in the cells. In the second iteration we select concept 0, 2, AB, and if we look into the table we can see that only one item is uncovered. So in the last iteration the concept 1 ACD is selected, and each concept has actual coverage equal to 0. So the computation ends with concepts contained in the set F. The older algorithms, GreCon and GreCon D, in this case returns the same factorization. GreCon and GreCon 2 always returns the same set of factors. Unlike GreCon D, sometimes returns different set, and it's because of different search strategy. Now let's look at the experimental evaluation. GreCon 2 totally outperforms GreCon, and in many cases GreCon D. GreCon D is faster on mushrooms and tic-tac-toe datasets. It's because of this dataset has a small number of attributes but a large number of concepts. In the future, we will focus on possibility how we can reduce input set of concept without affecting output quality. And we also want to create parallel version of GreCon 2. Thank you for your attention.